talk now at NICEF and Utrecht, which is the two logos you see here. And so yeah, I'll talk about how a different type of multi-messenger probe, which is gravitational waves. So it complements nicely with the previous talk. And I'll talk about how we use gravitational waves to probe neutron stars as well as dark matter. I can switch with this. And so since I don't think people know me that well here, I just wanted to say a bit about who I am. So I'm from the US, and I was raised in New Jersey. And I tend to enjoy like nature and travel and volleyball and hiking. And in terms of like my interest professionally, I collaborate with people all over the world. Kind of LIGO and Virgo make that easy because you can talk to people at any time in the collaboration. And I'm also heavily involved in activities for DEI, so diversity, equity, and inclusion. That's meant to make physics a bit more inclusive towards everyone. And so I specifically am involved with making physics more representative for LGBT people, and also involved in supervising students at all levels. And so that's what I like to do aside from research. And then in terms of my academic career, I studied in New Jersey, and then I did a joint PhD between Florida and University of Rome. And that was for 4 years, or 4 years or so. I also was able to live in Tokyo for a little bit as a visiting researcher. And then I did my first postdoc in Belgium at UC Louvain, which is right outside of Brussels. And then now I'm a postdoc in NICEF. And I'll basically be talking a lot about stuff that I did in basically this postdoc and the beginning of my current postdoc. But although I won't touch on stuff I've done in the PhD, a lot of the things that I've been working on are only possible because of the work that I did during the PhD. So I basically generalized a lot of the work I did during PhD to apply it to dark matter and different forms of, in different types of, and in neutron stars as well. And I won't talk about this in the talk, but I'm also involved in machine learning and stochastic background searches for neutron stars and early warning for neutron star in-spirals and next generation detectors. So if you're interested, like Nathan said, I'll be here for a couple of weeks so we can chat about this. And okay, so just to talk now about the research. So first I'll just give you some introduction and motivation. So what are continuous waves, why are they important, and how do we use them to probe the different types of physics that I've already mentioned. Then I'll go into the exact physics that we can probe. So basically gravitational waves from neutron stars as a way of probing the GeV excess. And then I'll talk about how we can use gravitational wave detectors to probe the existence of dark matter directly. So this is a coupling of dark matter to gravitational wave detectors. This is not a gravitational wave. And then I'll talk about gravitational waves from light primordial black holes that in-spiral slowly towards each other. And then finally about boson clouds that annihilate and give off gravitational waves if they're formed around spinning black holes. So with that, I'll just jump right into it. So just to define what continuous waves are, so these are quasi-monochromatic and persistent signals that are subject to typically a Doppler modulation. So they come from somewhere in the sky, and they're basically emitting at one frequency. And they're quasi because there's some mechanism that's causing the rotational frequency to change over time. We call this a spin down or a spin up. And unlike the types of signals that maybe you've heard about from LIGO and Virgo, that these binaries that merge, these continuous waves will last for a very long time. And so much, much longer than the observation run. And so this means that we can keep observing them. We can, if we actually detect one, we can keep observing them. And when we do detect one, this will be a completely new signal type. And this will then give us, in a similar way that the first detection of binary black hole merger opened up a huge branch of gravitational wave astronomy, the same will be true of continuous waves, that whether we detect a neutron star or we detect dark matter, this will have major implications for the fields, for multi-messenger astronomy as well as for fundamental physics. And just to give an idea of like how quasi-monochromatic are we talking about, here on the y-axis, you see the gravitational wave frequency. On the x-axis, you see time. And you see, essentially, a signal that's lasting for 2,000 days on the bottom panel here, where you see this overall modulation is due to the fact that the system is spinning down at some frequency. And then if you zoom in further, on the order of a year, basically, you see the Doppler modulation that occurs because the source is located with respect to the Earth, and the Earth is rotating around the sun, or is orbiting around the sun. And so you have this Doppler modulation. And then on this smaller time scale, on the order of a day, you also have the fact that the Earth rotates about its axis. This gives rise to a different type of frequency modulation. So this just sets the stage. And so just to give some context for this talk, there's so many types of continuous wave sources, and I will not talk about most of them. I'll talk about just the ones I mentioned before related to dark matter. But this is a field that when we detect something, this will be an extremely bright future. So we will be able to probe so many different types of physics with a simple model, a quasi-monochromatic signal. And due to some reasons that I will discuss later, there are so many algorithms that have been developed to detect these sources. And this is because the computational complexity of doing searches for monochromatic signals is actually quite a lot. And so there have been a lot of innovations as to how you can do this smartly and without a big loss in sensitivity with respect to the optimal signal processing technique, which is basically using a model you have for the signal and just correlating it with the data. So now, let me just describe what the principles are that we use to detect continuous waves. So if we're thinking about a neutron star, which is basically where this field originated, looking at isolated neutron stars, when we know the source location and its parameters, we can do a match filter. This means that we know everything about the source. We know its frequency, we know its frequency derivatives, and we know its location. And so that means we know exactly what the gravitational wave signal should look like, and then we just do a correlation of the signal model with the data, and we get some signal-to-noise ratio statistic out. That's not what I'll be talking about in this talk, because that's too easy in some sense, although it's not easy. But when we talk about things that we don't know much about, so if we don't know where a neutron star is, or we're looking for dark matter, we can't use this method because we don't know anything. We know very little about the source, and so we have to devise ways of essentially doing these kinds of analyses that don't rely on exact models of what the source will look like. And the principle of how you do these analyses are that you don't actually look at all the data at once. You look at the data in small chunks, and you analyze each of these chunks coherently, meaning that you have the phase information encoded in each of these chunks, and then you combine each of the chunks incoherently, so with the loss of the phase information. So you basically combine power in each of these segments. And so just to give you an idea of like why we need to do this, so if you think about a search for neutron stars coming from anywhere in the sky, the number of sky points scales with the frequency that you're looking at and the amount of time you analyze. So if you have a year's worth of data, that's like 10 to the 7 seconds, and a frequency of 10 hertz, you're talking about something on the order of 10 to the 16 sky points to search over at one frequency. So this is intractable. This is just way too many templates. And the computing cost basically scales with a very high power of how long you observe for. And so that's why we need these different methods. And so from these different methods, it turns out you can do not just neutron star gravitational wave physics, but also you can look for dark matter. And that's basically what the focus of my work in the last few years has been, which is to essentially adapt these methods that look for continuous waves from neutron stars to look for dark matter instead. So now, let me then just talk about neutron stars for a little bit longer, about some recent work that I've done, where we can actually use gravitational waves from neutron stars to probe the GeV excess, and at least one hypothesis for what could cause this excess of gamma rays in the center of the galaxy. So, yeah, yes, this slide. Mm-hmm.
Are we subtracting those periods and measuring the slope, or what?
So so the question was about if you subtract these periods, are you measuring the slope, and is that the goal? So, sorry. So what you actually, so you don't subtract. You essentially correct the data for a signal that's coming from some sky location. So you have your data your raw time series is essentially amplitude and phase, and so for each of these modulations, you know the form of it, so you can remove that from the data, and then what's left over is this this modulation here, do the spin down of the source. So it's not a subtraction; it's more of a correction.
So there, what's the physics is in the yellow line going down, right? The
Yeah,
rest is just because the Earth is rotating and moving around the Earth, right?
Exactly.
The sun.
Yep. The physics is
So
all here.
the physics is the slope of the yellow line, how
Yeah.
it goes down, right? So
Yep.
you want, okay.
Yeah, because as I'll explain a little bit later, from a neutron star, this information encodes the gravitational wave emission. So the rate at which gravitational waves are emitted is proportional to how quickly this source is spinning down.
And with the current experiment, as you explained, we did not detect this yet, but do we see just a flat yellow line constant, or do we see a yellow line going down, but we cannot see the oscillations?
Yeah, so we don't really so you do this correction for every sky position, and so what you actually see, and then you search over every kind of possible spin up or spin down that you would have, and so what you see is just essentially a signal to noise ratio that corresponds to each choice of these parameters. So it's not like you have you must analyze each location separately. So for each location separately, for each choice of parameters, you have a different signal to noise ratio, and with that, you say, okay, is it significant or not? So it's not exactly what you describe. It's a bit more. Yeah, I think it's a bit more involved than that. Because basically, for each, you have a frequency derivative, a sky position. And for each of these, you get some SNR, and this tells you if it's significant. And then you have billions or trillions of these, and then you have to understand if this is, to what extent you're looking at something that's real or not. And you have to do a lot of studies of the noise to really understand that. Okay.
Short, the idea is, if we understand well these factors, we can better subtract the noise from the rotation of the Earth. So.
Yes, and in fact, the noise doesn't have this Doppler modulation. The noise is on Earth. So you have some transient, you have like the 60 hertz line because you plug things into the outlets in the US. And this line gets, when you correct for the Doppler, this monochromatic noise line gets spread into many frequency bins because of this, because you correct for the Doppler. So yeah, it helps us to pull signals out of the noise.
Thank you.
No problem. Okay, so I'll move on now to the GeV excess. So the GeV excess, as I said, is a gamma ray excess that's at least two hypotheses for it. One is due to annihilating dark matter. Second is due to a millisecond pulsar population. And this is an interesting thing to probe with gravitational waves for a bunch of reasons. So one is the fact that there's no interaction of anything between gravitational waves that come from the center of the galaxy and us. So we don't have to deal with these, scattering effects or any kind of effects that are dealt with in the electromagnetic community. Furthermore, this is a probe of the GeV excess that's not dependent on electromagnetic probes. So, and we complement them, and I'll show you exactly how that happens when I talk about the results. Furthermore, there is a huge problem in that we don't see most of the neutron stars that we expect to exist in the galaxy. So we expect on the order of 1 billion neutron stars, but we see thousands of them. So this means that either there aren't neutron stars, that it could be something else, or that these neutron stars, most of these neutron stars are not emitting electromagnetically. And so then we can use gravitational waves as a different probe of them. Yes? It also could be the beaming. I mean, the fact that the neutron stars are, so the question was, could you also explain this discrepancy based on the beaming yes, of course you can, but I don't think the beaming fully accounts for the 6 orders of magnitude difference, but it could contribute to the difference, yes. Yeah, because in this case, they'd have to, I don't think statistically that it would, that 1 million pulsars wouldn't, or more than 1 million. Yeah, so many pulsars would be all beaming away from us. Furthermore, so now moving back to the GeV excess. So furthermore, when you model what causes the GeV excess, you are basically choosing a way to explain the observed electromagnetic emission based on some number of pulsars in the center of the galaxy. This is called a luminosity function. And so with gravitational waves, you can actually exclude the existence of certain luminosity functions. Whereas electromagnetically speaking, your result is a luminosity function that matches the profile of the GeV excess. And in this case, gravitational waves are able to say, okay, that this luminosity function predicts a certain number of pulsars in the center, but we don't observe those pulsars or gravitational waves, so therefore we can constrain this function as explaining or not explaining this GVXS. The other thing is that maybe more of a political thing, that since these are laser interferometers, LIGO, Virgo, and Kagra, all gravitational waves are heard by this instrument. And we point, which I alluded to before, we point to different sky locations at the level of data analysis. This means that there's no competition for telescope time or these kind of things that are potentially politically based or like scientifically interest based. But in this case, we can just look for different locations pretty easily. So now let me then talk about then how could neutron stars emit gravitational waves. So so neutron stars are basically very, very spherical because they have a very strong, they have a mass that's pretty on the order of a solar mass, but a radius of the order of 10 kilometers. So they're very compact. But if we can imagine that they're not perfectly spherical, and that there could be a so-called mountain on the surface of the star, and the size of this mountain, how big this mountain is what gives rise to gravitational waves. Essentially, the rotational energy of the neutron star goes into the gravitational waves that are emitted, and this causes the star to spin down. And so the size of this mountain is quantified by something called the ellipticity. This is the fractional change in moments of inertia normalized by the z component of the moment of inertia. And the mechanism by which this could happen is that there could be some very strong internal magnetic field, so inside the neutron star, so that we don't observe it, we observe the external one. There could be some temperature asymmetry that sustains this deformation. There are many models that explain how this internal ellipticity could be sustained. But what's conceptually important is that this ellipticity is extremely small. So we can basically measure on the order 10 to the minus 9-ish of this ellipticity. So if we say that of this ellipticity of order 10 to the minus 9, and then we say, okay, the radius of a neutron star, or the size of the neutron star is of the order of 10 kilometers, this means that we could basically measure a size of this mountain on the order of micrometers. Which is a pretty amazing thing when you think about it. And this also implies that the spin down is on the order of nanohertz per second. And this means that these gravitational waves last forever. They last for a much longer time than what we can observe for. And so with this in mind, what we can do is we can use results that come...
Sorry, where do these numbers come from? It's just some simulation? So the height of the mountain, for example, how do you know the typical height of a mountain?
You don't know this. So like you have some estimation of what the minimum could be, but this is very model dependent. But this number basically comes from search constraints. So you say, you can calculate if all the energy of all this rotational energy were converted to gravitational waves, assuming no electromagnetic emission, you could get a maximum value of this ellipticity, which could be on the order of 10 to the minus 6, 10 to the minus 7, 10 to the minus 8, depending on what neutron star that you consider. This is just meant to be an example to give a sense of what the size of the mountain could be.
But do you have any idea if it's stable or even that? Or
the mountain itself being.
Sorry?
Sorry, the mountain being stable or the. Yeah. I don't. It's not something that we consider. I mean, we just consider that there could be a deformation. We don't assess whether it's stable or not.
And if it's not stable, wouldn't that affect all the waves that it produces?
Yes, but I don't. What would make it unstable?
I don't know. I don't know what makes the mountain, but.
Yeah, I mean, so the magnetic field. If the magnetic field holds up the mountain, and the magnetic field is a constant value inside, then it should the size of the mountain should be stable. Okay. Think that there's not much is affecting the neutron stars over the course of their lives. I mean, once they are formed, they are basically spinning down forever. And so from electromagnetic observations, we know that the frequencies are pretty constant. And so if there were, I mean, they do glitch, so like this could happen, but we can kind of explain when that happens if there's some, but this is a pulsar-specific thing. It's not necessarily true of the whole population of pulsars. So if there's some like breaking of the crust that happens and then there's a huge spin up, then it wouldn't be stable. But eventually, even in this case, over a period of time, which is on the order of months or so, the pulsar eventually spins down to its original like frequency. So yes, I would say yes, they are stable.
Okay.
Okay, so now let's talk about a search. So basically what we can do, knowing this about neutron stars, we can say, okay, we're going to do a search for neutron stars somewhere in the sky, anywhere in the sky, and we don't see anything. And so what we can do when we don't see anything is that we can quote an upper limit, or actually we can quote the minimum detectable mountain size, or the minimum detectable ellipticity that would have had to exist at some distance away from us, such that we would have detected a signal. So in this case, here what you see on the y-axis is the ellipticity as a function of gravitational wave frequency, and you see different values. And this comes from an all-sky search. So, and this is fixed at a distance of 8 kiloparsecs, so about the galactic center. And so this doesn't tell you much on its own. This is just telling you basically that, you know, at a certain frequency, you would have detected a source with a ellipticity of at least 10 to the minus 6 at that frequency. But what we can do with this information is we can say, given this and So given this curve and given a distribution of frequencies of what we might expect for neutron stars in the center of the galaxy, and also given a distribution over what the size of these deformations could be, what number of neutron stars could we have detected in this survey? And so we calculate this in two ways. So we calculate it in one way, but there's two steps. So first is that you calculate the so-called probability of detecting of a millisecond pulsar in the galactic center. So this probability, you can think of it as like a fraction. So this is an integral over a probability density function of frequency and a probability distribution function of ellipticity, where the upper limits you saw on the previous plot come in the bounds. So at a given frequency, you integrate from that upper limit value to 1, so all ellipticity is greater than that, over some distribution that you have to assume. And you do the same thing for the frequency. And this is independent of any luminosity function, this function I described before. And in order to calculate what this distribution of ellipticities could be, you can decide, you can use the distribution of what you think the internal magnetic fields are of neutron stars, or you can say that, okay, I'm going to assume that some fraction of the emitted electromagnetic, I'm going to assume that not all of the rotational energy is going to neutron stars, but only 1% of it, or 0.5% of it. And with that, you can, by using the 18F catalog, which is this catalog of known pulsars, that's about a few thousand of them, you can compute what the maximum ellipticities are, as I mentioned in the response to Nathan's question, and you can say, okay, well, I'm not going to use that max ellipticity. I'm going to use a fraction of that, and that will explain the emission of gravitational waves. And so when you do that, you can basically assume different fractions of energy are being emitted, and then you can calculate this PGW as a function of the fraction of energy loss for different moments of inertia. And so you can see here that that if the fraction is very small, so this is like 0.01%, we have no chance of seeing anything. But if the fraction of energy is on the order of 1%, that's going into gravitational waves, then we have, well, this is a kind of number that's hard to really get an intuitive sense for, but we have more of a sense, more of an ability to see this. And that will become apparent in the next slide. So if we say, okay, I'm going to pick as test cases 1% energy loss due to gravitational waves and 0.5% energy loss due to gravitational waves. Then I'm going to say, okay, with that information, I'm going to calculate the number of millisecond pulsars that I could have seen using a luminosity function, which is electromagnetically derived. So in this case, this luminosity function tells you, for a given choice of parameters, the number of pulsars that you could have seen in the galactic center. And so basically, you choose two parameters, and you get this number. And if what number I calculated on the previous slide times the number of millisecond pulsars that is predicted by the luminosity function is greater than 1, you can say that you would have detected a gravitational wave in this all-sky search. And this is generic to any luminosity function. You pick a luminosity function, you pick the, and then you understand what parameters can give you this number. Then you use the gravitational wave results on the previous slide and calculate whether or not whether this NGW was greater than 1. So in the cases that as I've described, so now you have, what you can do is you can say, okay, I'm going to look at 0.5% and 1%. And so here is this is a plot created for 0.5% and then 1%. On the y-axis, you can see one of the parameters of the luminosity function. On the x-axis, a different parameter. And the color is the number of pulsars that is predicted. The blue region corresponds to which portion of the parameter space that gravitational wave observations can exclude. The white region corresponds to what Fermi has excluded. And so depending on what fraction of energy that you pick, you get different results. And so, but you can see that this is complementary to what Fermi does, because Fermi probes essentially this region of the parameter space, which is colored in white. And so this means that you can use gravitational waves to probe the excess. Yes, please.
No, sorry, I have a heuristic problem here. So the rotational energy of the star is an energy. The gravitational wave flux is an energy per unit of time. Sorry, what does it mean that one is a fraction of the other?
No, the fraction is this. You mean this fraction? This is
the energy loss due to the spin down?
Oh, this is, I mean like fraction of energy emitted via gravitational waves. So not a loss. Like I mean like not per unit time. Just like 1% of the energy is going to gravitational waves, flat.
Percent of the energy, or the kinetic energy loss, you mean?
No, 1% of the 1% of the rotational energy is going to. So okay, like the loss, like the ratio of
so you infer this from the spin down.
Yeah, so you guess what this could be from the spin down. If you assume that all energy goes into gravitational waves, you get the fraction is 1. But if you say, okay, I'm not going to consider all of it, but a lesser fraction, then you get the smaller numbers.
No, just so when you mean kinetic energy, you mean kinetic energy loss?
Yeah, the loss
from the spin down.
Yeah, so actually F dot is proportional to E dot. So yeah, it's the loss. Yeah. Okay. So then that's what you can do with neutron stars.
Just to understand.
Yeah.
This is from your PhD, or this is before your PhD?
This is after the PhD.
So and so the people in LIGO looking for this, is it just a small group, or is it?
No, we all look for this. I mean the
idea of looking for these fluctuations of frequencies.
LIGO looks for this.
I see, that's an old idea.
This is not a new idea. Okay. The new idea is constrained GeV excess.
I understand.
Yeah.
Okay, thank you.
Yeah. So now I will switch gears away from neutron stars and also away from gravitational waves and talk about the direct detection of dark matter with interferometers. So, the idea behind this kind of signal is that different types of dark matter will couple in different ways to the interferometer. And so this could happen if it could happen, and it could happen if the dark matter is ultralight, and the Earth is sitting in basically a field of this ultralight dark matter. And so why this happens? So you have an extremely large occupation number of these ultralight dark matter particles in any given unit of space. And with these ultralight dark matter particles, they have a finite coherence time. And they also have a finite coherence length. Or this coherence length is much larger than the separation between two Earth-bound detectors. And this is just a picture describing that. But for us, what this means is that you can model the superposition of plane waves. This dark matter is a superposition of plane waves whose velocities follow a Maxwell Boltzmann distribution. And this means that you have some frequency fluctuations on the order of a 10 to the minus 6. And this is coming from the fact that this is the velocity of dark matter at which that it's flowing through us, that the dark matter is orbiting around the center of the galaxy. And so this is the type of dark matter that could, so this is just generic. I have not specified what kind of dark matter could actually interact like this. But this is generically true for any kind of ultralight dark matter. So how it could interact, so if I will focus on one case, which is a vector boson particle or a dark photon. And so this is a gauge boson. that would interact weakly with protons or neutrons in the mirrors of the LIGO-Virgo interferometers. And so this will couple with some strength given by epsilon sub d and to the mirrors. And so essentially what happens is that there's two ways in which the signal is detectable. The first way is that there's a differential strain that results from a spatial gradient in the dark photon field. So what that means is that since the detector exists in a field of dark matter, and each mirror is in a different place with respect to the incoming field, the dark matter will essentially move the mirrors in a slightly different way. Where this dark photon, you can think about this dark photon as causing a electromagnetic field that moves the mirrors in a particular way, and in a quasi-sinusoidal way. That's why this is also a continuous wave. And so this is, and then what matters in LIGO and Virgo is that you have the differential strain, so a difference in the path lengths of the laser lights that's shining down each arm. And so that's what you have, and so that's one way that you get the signal, the fact that the mirrors are in different places. The second way is that is a temporal way, where you have an apparent strain that results from a finite light travel time effect. Essentially, the end mirror, if the end mirror is within this field, it may move in a time. It will move over time before the light from the input mirror has reached there, and this gives rise to this apparent strain effect. And so, like, since it takes light a finite amount of time to travel between the input and the end mirror, and the mirror moves in that time, you also get an enhancement of the signal due to this the finite light time travel. And I can go into more details later if people are interested in that. So I basically developed a method of searching for this type of this signal. So the method essentially is that you start with the strain data, which is this h of t time series, and you basically create a time frequency spectrogram from that. And this involves taking Fourier transforms of a different lengths, call them TFFT. And for this method, as I mentioned before, the dark matter has a finite coherence time. A finite coherence time here. And this means that if you observe for longer than this coherence time, the signal is not monochromatic anymore. It actually splits into many frequency bins. And so that means that this method basically chooses the analysis coherence time to match the signal coherence time. And so this means that the signal is basically confined to one frequency bin for the entire time that you observe for. And that is given, so here you see a frequency time plot where the color corresponds to essentially the FFT over the noise. So it's some measure of the power in any given pixel. And you see this is an injected signal, so it's not real. And it's given here. And the method essentially integrates this time frequency map over time, so projecting it onto the frequency axis, where you get a plot that looks like this, where this is the number of, essentially the number of times in this plot where the power exceeds a certain threshold. And that's what you have plotted here. And so you can see the signal is quite prominent. This makes sense because the signal is really strong. In practice, it will never be this prominent. This is just an example. So with that method, I led a search as part of the LIGO, Virgo, and Conga collaboration to look for this type of dark matter in the most recent observing run. And just to give you a sense of what the noise looks like, the noise is very, very disturbed. And many of the outliers that we get after doing this kind of analysis don't actually come from real signals. They come from some noise disturbance. And there were 11 outliers in this analysis, and we were able to veto them all. One of them was due to a large comb in I think it was H1, the Hanford detector in the US. And so what is a comb is this, like, if you can imagine actually a comb, and it's just like a bunch of frequency disturbances that are evenly spaced. And you can see that this outlier is probably arising from this kind of disturbance. And so these are the kind of things that we have to do and when we do these kind of analyses. And so in terms of what we got out of this analysis was a constraint on the degree to which dark matter will couple to interferometers. And that's given on the y-axis here. as a function of frequency. So this coupling constant is normalized by the electromagnetic coupling. So this really means that the strength of this coupling is 10 to the 45 times weaker than the strength than the square of the electromagnetic coupling, and so you can see this is plotted both in terms of frequency and mass. So we're talking ultralight masses here, as you can see by the plot up here, and you can see that the curves from our method. So one was a cross correlation based one that was also run in this search. That's in red. And the other one is in black and blue, which is the method that I designed for this search. And you can see that in both cases, and then the other curves correspond to existing experiments that search for this type of dark matter. And you can see that above 100 hertz or so, that the limits from our search exceed by a few orders of magnitude the existing experiments. And this is, again, something that was never designed to search for dark matter, or at least direct detection of dark matter. So this is a pretty impressive result, given that LIGO and Virgo were not designed for this purpose. And I will just mention that there are other types of dark matter that can be searched for too, and dilatons, axions without magnetic fields, so without using a huge magnetic field, which is very interesting. And these types of dark matter will leave a similar imprint on the detector. But they will couple to different things in the detector. Like dilatons will couple to the electrons in the beam splitter and change the mass of the electron and stuff like that. Each of these has a particular way in which it interacts. But because of this, because there's different ways that dark matter can interact, how do we know which dark matter we would actually see? So another work that I pursued after this was trying to understand if there was any way we could distinguish these types of dark matter and their interactions. And so we designed a method on the basis of the Wiener filter, which is essentially, it's not really a match filter for stochastic signals, but it basically allows you to do some kind of match filtering for a stochastic signal. And it essentially minimizes the mean square error between a modeled random process and what you observe. And so our detection statistic in this case is a residual. So it's related to this essentially calculating cross power between detectors, where X and Y are the different detectors that you would use, and normalized by the autocorrelation, I think, of the signal. And so you can do this. And so you basically, when you have a signal, so this is a plot of this residual as a function of frequency in a particular band for an injected signal. And you can see that when you have, at the frequency of the signal, you see that there's a dip in the residual. And so that means that this method with the Wiener filter can not only be used, so it can be used to at least find a signal, but can it be used to distinguish? And that's the question I will ask now. So in this study, we simulated two types of dark matter that could have interacted with the interferometers. One is a scalar interaction, so moving the beam splitter, just like changing the size of the beam splitter. And the other is vector dark matter, so this dark photon dark matter that I already discussed. And so here you can, so if you do this kind of study, you expect that if you use the wrong model, you'll get a residual of 1. So there's no indication that the signal is in the data. And so on the y-axis here, you have the Wiener filter residual as a function of frequency. And for different combinations, you inject a scalar, you filter with a scalar. You inject a scalar, you filter with a vector, and so on. And so you can see that the residual is basically 0, so you're sure the signal is there if you filter a scalar and a scalar. And a vector and a vector as well. Although the vector signal is much weaker, that's why you don't see it so prominently. But when you filter a scalar with a vector or a vector with a scalar, you see the residual lies about 1 for each of these ejected signals, which are at these frequencies here. And this means that, assuming your model is correct, that you will be able to differentiate between these types of dark matter interacting. And this is a plot that says, I think, the same thing, but I will move on from this. Yeah.
Suppose neutrinos don't do something similar? I mean, how do you distinguish dark matter from just other kinds of particles? I'm sorry, I'm missing.
Yeah, so the one thing is this stochastic modulation. This is a pretty key thing. So the fact that the dark matter is moving at a finite speed, that this 220 kilometers per second, this gives rise to this fractional frequency change that we won't observe in other types of particles. And
Why does dark matter move at different velocities?
no, the dark matter moves the dark matter moves at one velocity, which it's if the dark matter existing, it's moving around the center of the galaxy at a fixed velocity, this virial velocity, and so it's one velocity for this type for dark matter, and so at least the local dark matter, and so yeah, like so because this velocity is finite, the frequency modulations are finite. And they're different. So neutrino moves at a different speed. It would have a different imprint, I would guess. But it's also it's a physical thing. Like it's coupling in a specific way to the interferometer. So the stochastic modulation is just the kind of like in the phase, but the way in which it's coupling that will actually give rise to the signal. So unless neutrinos can couple in this specific way, we wouldn't be sensitive to them. Okay. So, so you can also, go ahead.
Andrew, can I ask a question about the coupling that you just mentioned?
Yeah,
so,
yeah.
So can you explain a little bit more the coupling? Because I suppose if it's a dilaton candidate, it couples to the trace of the energy momentum tensor. If it's an axion, it couples, I don't know, differently.
Yes.
Can you just explain a little bit more what you have done?
Yeah, sure. So, so the methods that I've worked on have been specifically for, well, we've applied the dark photons, but they could be applied to any of these types of coupling. So, but let me think of how to explain. So, so let's start with the dilaton. So the dilaton will, so if you imagine that I'll just use this eraser. So you have an interferometer, and this is your beam splitter. This is the end mirror. So for the dilaton case, the dilaton will couple to the electron mass, or the electron, and the photon. And so each of when this coupling happens, the atomic Bohr radius, I guess a naught, this will change. And so the size of the beam splitter will change. And if we zoom in on the beam splitter, this is again the interferometer. We zoom in on the beam splitter. If the size is changing, so it's oscillating. The dark matter is a plane wave. It's oscillating. So that means that the light that comes down from this mirror will travel on a different path, because this is moving that way, this is moving a bit that way. The light will travel a different length this way compared to that way. This gives rise to the differential strain, and that's why dilatons can be detected with the interferometer. And so actually in this case, the length doesn't matter. It could be like a tabletop experiment. What matters is the material of the beam splitter, how this coupling happens. In the case of axions, go ahead.
Ricardo. I have one.
Right. Right, but the effects are like the major effects of the change in the size are happening at the beam splitter. They're happening also in the mirrors, but a few orders of magnitude weaker. There are a few orders of magnitude suppressed compared to what's happening at the beam splitter. So for this type of dark matter, only what matters is at the beam splitter.
I don't know what the words mean. So I know what dilaton, I assume that couples to the metric and it changes it rescales the metric. Is that why you call it
I think so. I mean, I kind of just know that it couples to the electron and it changes the velocity, but I don't know the theoretical. I don't know theoretically like what it's exactly coupling to in the Lagrangian or.
But you know why it's called? I don't know what you call it. Dilaton.
Dilaton. I don't know. I mean, I think it also could be just scalar dark matter. I don't know why it's called dilaton.
Okay, but you claim once you say the word dilaton, you know how it couples to the electron? That's the claim?
I think it's just as ambiguous as the dark photon, because the dark photon can refer to different coupling mechanisms. So I think it really depends on who you talk to and what the meaning.
Okay.
In this case, the dilaton for me means this kind of coupling.
Okay,
But
so just to make sure, it's
Yeah.
not the coupling to the metric, it's the coupling actually to the standard model that's
yes,
relevant for you.
it's the coupling to the
Okay.
standard model.
Okay, thanks.
Yeah.
It doesn't couple to protons?
This one, I don't think it does. No, I think the dark photons couple the protons, but I don't think this one does. I think it's just the electron and the photon. You have changes in the mass and changes in the fine structure constant that result from this coupling. So I don't think it's the proton, no. Any other questions?
And then this changes periodically because of the frequency of the plane wave.
Yeah, exactly. So
And
it's oscillating. And
so this deep there is because of the mass of the dark matter.
so this dip, so this is yes. So like this dip occurs because you have basically matched the templates of your signal with the correct frequency of the dark matter in this like kind of stochastic way with this Wiener filter. So this statistic that you get, the Wiener filter residual, it's close, it's 0. So it means it's an exact match.
Right. So you
Yeah.
you inject this signal of this mass and then recover this mass.
Yes.
Okay.
Exactly. No problem. And then you mentioned, you asked about other types of dark matter. I will just say that the axion, will affect the phase velocity of the light that moves down each arms. And this will in turn lead to a differential strain because depending on what the mass is, you have different speeds, you have different path lengths that are carved out by the light. And this is also measurable. But I think it's measured in a different channel. So it's not this differential strain channel, but it's measured in a different one that enhances the sensitivity. But yeah.
That's not in the beam splitter then?
It's not in the beam splitter, no. Only the dilaton is in the beam splitter. The other types of dark matter, they rely on the arm lengths being extremely
that's
long.
what Ricardo was mentioning.
You meant the other types of dark matter. Okay. Okay. So now I guess I can move on to another cool thing that you can do with this type of dark matter. And let me then just give some context. So these kinds of methods for continuous waves, they are not just limited to one detector or one even type of physics, as I will show throughout the talk, but they also have applications in the future. So to analyzing LISA data when LISA flies, or when analyzing Einstein telescope data when eventually they build a future third generation detector. And so something I wanted to understand was, can you detect ultralight dark matter in LISA, and what problems will you face in the future when you do this? And so you can, in principle you can. So this was a project I worked on at ESA, and essentially you have the same kind of coupling that you have to, so for dark photons you have the same kind of coupling, so this dark photons coupling to baryons, but the difference is that the masses that you're looking at in LISA Pathfinder or LISA are much smaller. So you can see here so this is a constraint again on the coupling strength as a function of the dark photon mass. You can see that the masses are a few orders of magnitude lower than the previous ones, the ones on the previous plot. This is not fundamental. This is only because the frequency range of LISA is a few orders of magnitude less than the frequency range of LIGO and ground-based observatories. So the point is that you can apply the same CW techniques, the same continuous wave techniques, but they have to be modified a little bit because when you have such low masses or low frequencies, you have specific problems like not so much sampling down here at the low frequencies, and you also have this. So from the perspective of someone doing analyses for merging black holes, you have non-stationary noise and you have gaps in the data, which are things that, at the moment, the signals that LIGO detects are very, very short, on the order of a second or hundreds of seconds, where these things don't matter that much. But in the future, when signals last a lot longer, they will matter. And so the kinds of methods that have been developed to search for dark matter can be well, not, I wouldn't say easily, but they can be applied to searches for dark matter in space-based telescopes, but also a variety of other types of physics or types of gravitational waves. So now I will go back to gravitational waves and talk about light primordial black holes, and I'll define what light means. So just to give you some context, so within the LIGO and Virgo collaborations, and I was also outside of them, there have been a lot of searches dedicated to so-called subsolar mass primordial black holes. So this means that they search for basically primordial black holes that are equal mass. They're in a binary. They're inspiraling slowly towards each other, or not too slowly, but they're inspiraling slower than the 20 solar mass black holes. And you basically you look for these types of signals. You do the match filter. You don't find something, and you set a constraint on this fraction of dark matter that primordial black holes could compose as a function of the black hole mass. And these are for equal mass binaries. And so that's something. And this is very good. But the mass of the primordial black hole could be anything. Just like the mass of the dark matter particle can span many orders of magnitude. And there have been no searches of gravitational waves for primordial black holes with masses of this order. And so why? The reason is because to do match filtering in this regime is really expensive. The signals are long. They have higher level complications, especially if they're eccentric. And really, the long part is the killer, because you have, when you do match filtering, you create a set of templates, a set of models that you correlate with the data. And when you have a long signal, the phase mismatch between each model accumulates more and more with time. So when you look for longer signals, you need more templates, you need more models. And that's why this range is pretty intractable at the moment. To give an idea, these signals will last maybe 100 seconds. And the signals that we want to search for, they can last on the order of hours to years. And match filtering can't do this at the moment. And so that's why they're continuous waves, the signals in this regime. They are long-lasting, they are quasi-monochromatic, or as I'll describe, they were also power laws, and we can then use the same kind of methodologies that I've already spoken to you about in this seminar to look for this type of primordial black holes, this type of inspiral. Okay. So this is just an overview plot again, just to give an idea. I will just say that this FPBH is constrained as a function of the primordial black hole mass, but these constraints are model dependent, so that they could be changed or evaded if you change the formation mechanism of primordial black holes. And so these constraints, as well as the constraints I present here, they must be taken with a big grain of salt, because they are model dependent. And so you have to be careful when you weigh the importance of these constraints. And so given that, so let's focus now on very, very light primordial black holes. So masses on the order of an asteroid, 10 to the minus 9, 10 to the minus 10 solar masses. So in this case, you have signals that will last for an extremely long time, just like a bump on a neutron star. These primordial black holes that are 10 to the minus 9 solar masses that are probably the size of a millimeter or a micrometer, they will be inspiraling forever. And when you understand that, then you say, okay, these signals are essentially like a continuous wave. They are a fixed frequency with a small spin up that's due to the fact that they're inspiraling slowly. And if you then say, let me then do a search for them, you don't actually have to search for them, because the all-sky search I showed you in the limits I showed you in the past, you can apply them to constraints on primordial black hole inspirals. If you only allow for linear frequency evolutions, and you say that the maximum spin up that you will search for, that you will allow for this inspiral to happen, is on the order of megahertz. This then gives you fixed ranges for the chirp mass, which is the script m, and the frequency. And from this, you can take the upper limits that come from a continuous wave search. This is h naught. So it's a strain. It's basically a delta L over L upper limit. And with the beam pattern function in there. And you can translate this to a distance at which you could observe primordial black holes. And with this distance and having no detection, you can then translate this into a rate. And the rate is only based on observation. It's not based on any primordial black hole model. With the rate, you can then assume that primordial black holes formed in some way, or that they are equal mass, or that they are asymmetric mass ratio. So in this case, we assume that there is one component mass, which is 2.5 solar masses. So that's the thing that we know a black hole could have this mass. And the second mass, we allow it to vary between the values that you see here. And so here you can see that, and so when you allow this, when you pick M1, and you have the distance, you have the rates, you can then calculate what is this F tilde, which is essentially a quantity that relates to the fraction of dark matter that PBHs could compose. And that's given on the y-axis as a function of M2. And so this is a fraction. You'd hope the number is less than 1, but in this case it's not. And this is because the limits themselves that we get from continuous wave searches are not yet constraining enough to put a physical limit on this F tilde. But this is okay in the sense that the detectors will improve in sensitivity, and this is only a factor of a few away from 1. So we hope in 04 or in 05 that you will be able to make a constraint on this asteroid mass region. But that's okay. I mean, so then this says, okay, that we can't constrain, well, this region, this asteroid mass. So let's look at higher masses. Can we constrain that better? And so then if we look at higher masses, so we look at masses on the order of 10 to the minus 5 solar masses, 10 to the minus 4 solar mass systems that are in spiraling, we enter a different regime, which is not a quasi-monochromatic regime anymore, but a regime where you have so-called transient continuous waves. So they're basically power laws. So the signal frequency evolution follows a power law, and it lasts for hours to days. So this is kind of an in-between. In between the types of mergers that LIGO has detected so far, and these quasi-monochromatic, forever lasting signals that are called continuous waves. And so in this intermediate regime, you have signals that are shorter but are stronger, and you can look for them. And the way that we essentially have a very basic model for this frequency derivative, as this frequency derivative is essentially proportional to the Chert mass and the frequency. And there are higher order corrections. We do not consider them here because at this point, the method works for purely Newtonian orbits, but we are also in the process of generalizing it. And this method can basically look for systems that are far enough away from coalescence and essentially not too relativistic. And so just to give an idea, this mass range gives rise to signals that are very long-lasting. I think I've made this point already. So I will just say that I will just then jump to the next slide where we actually have a method, where we designed a method to search for these long-lived signals. So this is based on the Huff transform, which is a pattern recognition technique that essentially maps points in one plane, points in this time-frequency plane, that fall along a particular curve to lines in a different plane, which is the Chert mass frequency plane of the source. So let me go back and just explain a bit. So this is a time frequency representation of an inspiraling primordial black hole system, injected, so fake. And this is frequency versus time. And so what you have here is a collection of points where you labeled by color, but really what we actually do is we don't actually consider the power at all. We just consider whether or not the power is above a certain threshold. So if it's above a threshold, a time frequency point gets a value of 1. If it's below a certain threshold, the time frequency pixel gets a value of 0. And so what we basically do in the Huff transform is that you, let me move this. You have a bunch of points in this time frequency plane, and you want to find what curves would these points lie on. Each curve corresponds to a particular frequency and Chert mass. So this curve, or that curve, or this curve. So then you essentially sum along these curves, and you put the sum in a two-dimensional histogram where this corresponds to one frequency and one Chert mass. And you loop. So you loop over all the possible frequencies and all the possible chirp masses that you consider. And when you do this, you take a picture or a time frequency map, and you transform it into a two-dimensional histogram where you essentially localize the power into one bin, where in this case your bin is a frequency and chirp mass point. Whereas before you can see that the signal is spread over many times. In this dew plane, it's integrated over time, it's in one bin. And from here you can do analysis. You can say, okay, is this significant or not? You calculate a signal-to-noise ratio, you calculate the backgrounds, you calculate the background here, and you assess whether or not it's significant. And so with that in mind, we know the method works, and we've used the method in many, so I've used the method in a search that I haven't talked about in this talk, but this method I developed in my PhD, and I have generalized it in my postdoc to look for these kind of inspiraling systems. And you can, so we know that so then we say, okay, how good can we get with this method? So what kind of constraint would we expect if we do a search with this method? So on the y-axis here, you see this FPBH. On the x-axis, you see the chirp mass. And the different curves you see correspond to different distances away from us at for different detectors. And so you can see if we look at the higher chirp mass this is for LIGO, for advanced LIGO, you can see that for a good portion of the higher chirp mass parameter space, that we are able to set a constraint much below 1. And so this is good. So like these kind of methods, these continuous wave methods can be applied to search for primordial black holes, just that you have to look carefully. So you have to look at a certain chirp mass regime and a certain closeness to us. Okay. Then I'll just talk about one existing adaptation that I'm working on with now he's a professor in Beijing, and so you can also this frequency huff, this huff transform, like I mentioned before, it only cares about the chirp mass. So when you have a chirp mass, you can essentially imagine that you have a system that is M1, M2, but as long as you generate the same chirp mass, you can describe the system. So in the language of match filtering, the chirp mass enters predominantly, or at least I think at a lower order than at a much lower order than the M1, M2 or the mass ratio. And so for us, the chirp mass is the chirp mass can mean you could have M1 and M2 be any combination such that if you that will generate the same chirp mass. So it's degenerate. And so then we can say, okay, can we use the Huff transform not to just probe equal mass primordial black holes, but can we also extend this thinking to so-called mini emery systems? So this would be one object with like 10 solar masses, something that we understand, that we know exists, with a much smaller companion. So something like 10 to the minus 3 solar masses. And so in LISA, this would be called if the masses were increased by like a few orders of magnitude, this would be called an emery, extreme mass ratio in spiral. For us, we call them mini emeries because they exist in the LIGO band, and their masses are smaller than what we expect in LISA. So to give you a sense, this is a plot about essentially the strain amplitude of the signal as a function of the frequency. And so you can see here, this is the path that a mini emery system would trace as it gets closer and closer to merger. This is 10 years for merger, 1 year for merger, 100 hours, 1 hour, etc. And so you can see that it's falling very much into the A-LIGO design sensitivity curve, and these different curves correspond to if you include relativistic corrections or not. So the part of this work was to understand if you include these relativistic corrections, can this method based on the Huff transform be sensitive to or robust against these corrections? Because the Huff only cares about the chirp mass. It only has this like 0th order Newtonian, it just assumes it's a Newtonian orbit. But we know in real life that these systems will they could have eccentricity, they could have relativistic effects, and we wanted to understand if to what extent they would be able to probe these kinds of effects. And we found that you can essentially probe up to on the order of hundreds of megaparsecs depending on what the mass ratio is between the primary component and the secondary component. And the color here is just the amplitude of the signal. Okay. How am I doing on time? Yeah.
So did I understand correctly that in the very beginning of your talk, the idea was to filter out the noise from these modulations whose origin was not physics, but rather the Earth and stuff rotating? Then the idea would be that this, my understanding was that this was not done yet, but you showed that in principle it could be done. And once this is done, then the very same methods can be used now to look for oscillations that are physical, that signal new physics, where the period is not just a day or a year, but rather something related to the time of these small black holes that they rotate, or the dark matter wavefront, and so on.
Yeah,
This
yeah.
is true?
It's mostly true. So like certainly for the neutron stars, you filter out this modulation due to the Earth orbiting, and then you can look for the signal. The ultralight dark matter, it's not affected by this kind of modulation because it's happening at Earth, like it's coupling to the detector itself. The primordial black holes, yes, this kind of removal of the Doppler modulation, allows you to do these kind of searches for gravitational waves. But I didn't, the modulation removal has been done way before my time. So this is like the things that you can do after the modulation is removed, that's where my work has focused on. But the modulation removing is like a standard technique that's been around for 20 years, 30 years. So it wasn't me. But yeah, it's a very important one. That's why I wanted to talk about it. And it's also relevant in this part of the talk. This is the last part of it, and we hopefully maybe have some discussion. So we can also use gravitational waves to probe dark matter clouds around spinning black holes. So what's the physics of this situation? So essentially what happens is if dark matter exists, if dark matter is ultralight, and if dark matter is the right mass, where the right mass means that its constant wavelength is of the order of the size of the black hole that's rotating, you can essentially have a superradiance effect happen, where you have a dark matter particle that pops into existence near a black hole. It gets bound to the black hole, and it scatters off of it. So it scatters off of it, and then it's bound to it because there is a strong gravitational force that's acting on this dark matter particle. And it can be shown that this happens in an exponential way. So you scatter one particle, and you just keep scattering more and more particles until this macroscopic cloud builds up. This cloud really is macroscopic. I think it's probably as big, if not bigger, than the black hole. And so this could happen if the conditions I mentioned before are true. But there are no gravitational waves that come from the building of the cloud. Where the gravitational waves come from is from the annihilation of these bosons into gravitons. So why does that happen? That happens because there's a so-called superradiance condition that essentially there's a maximum amount of rotational energy that the dark matter can extract from the black hole. And so essentially this cloud spins down the black hole. And after this condition is no longer satisfied, the cloud exists, and it doesn't extract more energy from the black hole. And at this point, we have to assume that the cloud, will deplete. So it will deplete over time, and so it will couple to gravity. The two bosons will annihilate into a graviton or a gravitational wave. And there's one other subtlety here, which is that the physics that govern the growth of this cloud are actually exactly as the energy levels of the hydrogen atom. And so everything you know about the hydrogen atom can be applied to this cloud. And this means that the energy levels are quantized. And so at each energy level, so we will only care about the first one usually for the scalar boson clouds. But for each level of energy, there's so the energy is fixed. The bosons annihilates, and they emit, therefore, monochromatic waves because the energy is fixed, and of the energy level is fixed. And there's this quasi-nature because of a classical effect that as you emit more and more gravitational waves, the cloud contracts. It spins up because it contracts, so it spins up. And so now I want to just address, so is it reasonable to see these systems? And the answer is yes. So the time for the cloud to grow is much, much less than the time for the cloud to annihilate. And for at least for scalar boson clouds, let's give them by these equations here. So for the same parameters, you have instability, the growth of the cloud on the order of a month, and the gravitational wave emission timescale on the order of 10,000 years. So if dark matter forms around black holes, we have a decent chance of seeing them. And so you can approach these kind of searches in two ways. You can look for known black holes, so like you LIGO and Virgo to detect black hole mergers. You can say, okay, I'm going to modify the waveform as if there was a boson cloud around them and see if I would detect the signal or not. That's one approach. This has its benefits and drawbacks. The biggest benefit being it relies on observations. That's pretty nice. But the other way you can do it is you can say that they're isolated black holes that have formed in some way. You don't care how they formed, that they exist. And so we performed so the LIGO Virgo collaboration performed an all-sky search for these boson clouds around depleting black holes.
Gases around black holes? Is this something similar, or is it something different?
It's like, I mean, it's like a particle. I don't know if it's. I don't think a gas is the right word, but it's kind of like an energy cloud. I don't know how you even describe it, but
But why is it different from a gas?
What is it? Oh, they could, yeah. It depends on. There are many ways that either they could annihilate, or they could also have a weak, strong, or intermediate self interaction. Just depends on the model. We don't consider, but this would affect the cloud, yes. So this is assuming a naked black hole. So, but yeah, these things would affect. It's just that these things are hard to model, and we don't know how it would affect in the first place.
I just don't sorry, I'm not in the field, but I just don't understand why everything has to be dark matter. Why can't it just be anything? Who cares what kind of boson it is? Or is there something special about these boson clouds that are different from just other kinds of matter?
So well, I guess like when you write down the Lagrangian, there's a particular way that the coupling happens. So
Sorry, but I can write down any Lagrangian because we don't know a Lagrangian. So
yeah.
So I'm just asking: is there any reason this is different from just ordinary matter? Is there some special property of this boson that's different from properties of just ordinary matter?
I can't really the self interaction maybe. But I don't know. I mean, we use this language, but yeah, I think if you can write down an equation that describes something that you don't have to call it a dark matter particle, probably it's valid. It's just that we talk in this language because maybe it sounds more.
You sell it to people to say it's dark matter.
Yeah.
Okay.
You sell it, yeah, but.
It has to be ultralight.
Ultralight. That's the other thing. It has to be ultralight.
Gases are ultralight or not? And I'm missing something, but okay, keep going.
Well, we can also talk more later if you want.
Sure.
Yeah. But there is certainly this, like, it's a good point to raise. Like, there's a lot of like politics in how we cast certain things, and yeah, I think that one of the ways that we choose to cast things is in terms of primordial black holes or in terms of this cool type of dark matter. But everything I've talked about, like with primordial black holes, is just objects with a certain mass that inspiral. It's generic. I mean, we just call them primordial black holes because we can't think of any other word for them, and it's trendy. But yeah, it's just that's kind of the reality. I think of a lot of people should be more honest about that in science, actually. But it's just how people work, I guess. But so yeah, okay. So we did this search. So in this search, I led the management of this search, which in LIGO Virgo there are processes for how you do the search, who's doing this, who's analyzing the search, who's reviewing the search, who's writing the paper, etc. So I was basically in charge of knowing everything about that and also contributing to the analysis when I could. So just to give you an idea, and so what comes out of this kind of analysis, of an all-sky search is exclusion regions. So basically, you do this kind of search for a black hole with a cloud somewhere in the sky. You don't find anything, and then you can set a constraint. So how do you do this? How do you set the constraint? You say, okay, let me assume that the black holes are some black holes are a distance of 1 kiloparsec from us. They have a very high spin, and they're a certain age of the black hole. If I make these assumptions, you can determine which boson mass and black hole mass pair that would give you an amplitude that's higher than what is detectable, that you've measured to be detectable. So your amplitude of gravitational wave from boson cloud is greater than your upper limit amplitude, which comes from a quasi-monochromatic signal. So here you have boson mass as a function of black hole mass for different age systems, and these colored regions correspond to masses that have been excluded from existing based on the search, and with different ages and different distances. And so this makes no assumption about what the underlying population of black holes is. It just says that at this distance and this and this spin, we don't see these black holes would be excluded. To actually fold in population information is a bit trickier and is certainly much more model dependent. We also present these constraints, but they are, they are less agnostic. So that's why I don't present them here. So I will just conclude by saying that's like these continuous waves, they are great ways of probing a variety of astrophysics, multi-messenger astrophysics even, and fundamental physics. And everything that has been done in this talk is using a very simple signal model. So basically having a sinusoid with a small frequency change over time. And so that's the beauty of this kind of work, but it's also its major drawback, because when you want to answer more fundamental questions, you don't have the tools to do it because you've assumed so little about the physics of what's going on behind the signals. So as a collaboration and also as like a group that works in this, we really have to start thinking about how to interpret possible detections and what that would mean for, say, the equation of state of a neutron star, or if we detected a subsolar mass black hole, what kind of other information would we need to really confirm that detection? And so these are the kind of directions that I would hope to go in the future. But I'll talk more about future directions at the Chalk Talk, I think, on Thursday. And so, yeah, and if you, and just to highlight once again that these detectors can probe not only neutron star physics, but also dark matter physics, or any matter physics, if you prefer not to use the word dark matter. And the types of methods that I presented in this talk, they are not as good as match filtering, but they are much more computationally feasible, and they really allow us to do these kinds of searches. So at that point, thank you. Thanks for your time. Thanks for inviting me here. It was really a pleasure to be here. So thank you.
Probably the same question that I asked already. So this first modulation that you explained, people of course knew that the Earth rotates around the sun before LIGO. So indeed, they were subtracting out these big oscillations. But then you are pointing out that inside the signal there are much smaller oscillations that are harder to see. And those, even though conceptually they are the same oscillations, but they have different periods and so on, and they capture lots of new physics. Right?
Yes.
And then instead of just doing Fourier analysis or something, you also have new techniques for extracting them out that are better and faster.
Yeah, they rely on Fourier analysis, but they're not this like match filtering, like exact correlation.
Okay, cool.
They're not so happy with it, but it's starting to become more popular. Maybe you can comment, but yeah, I mean, I've used it like during my PhD, but actually run like end-to-end search with it. But it's kind of still a black box. It's not like in particle physics where I think machine learning is quite widespread. it's only used in like one continuous wave search, and yeah, I don't know where else it's really used. I don't think they like the black box nature of it. It's political. I don't think it's, but